All right, and looking here, we have ourselves an octagon. We know that because it has 8 sides, and oct means 8. Let's check it out. Make sure we have 1, and the opposite side 2, 3, 4, 5, 6, 7, and 8. That's how we know we have our 8 sides. So we have our octagon. Our question here is, what is the sum of every single interior angle of this octagon? We're going to use our ideas about triangulation and knowing that all triangles have a interior angle sum of 180 to help us solve this problem. After this, we're going to kind of take a look at exterior angles and all those things. But first, let's find out the sum of every interior angle. A couple things that we have been checking out before. We know that every single triangle, no matter degree, no matter how long any side is, we know that every single angle, angle 1 plus angle 2 plus angle 3, is equal to 180. So we have proven that before. We've put them all into a straight line. We've kind of calculated some of those things. We've seen that before. So we're going to use that same philosophy and that same mentality to find angles and interior angles of many different shapes. So looking at this octagon, we're going to apply what we know about triangles and use our triangulation technique to help us get there. Now, before we kind of keep moving through these, we got to make sure we're not adding or increasing any angles. So that means every triangle that I want and that I want to draw is going to incorporate one of these exterior angles. I'm sorry, I said exterior angles, one of these angles that make up the octagon, so forming one of these interior angles of that octagon. So as we kind of go through that, I want to make sure that I'm drawing triangles that are included with every part of that octagon or every angle of that octagon. So as I create my triangles this way, obviously right now these are imperfect triangles because I'm just drawing with my finger, but if we connect it with a straight edge, we'd have now 1, 2, 3, 4, 5, 6 triangles, all having a representation of 180 degrees. So if we just take 6 times 180, we'll have ourselves an answer. And as we can just plug that in really quick, 6 times 180 will get us a sum, or a total of 1,080 degrees in the entire octagon. So that means now this angle plus this plus this plus this plus this plus this plus this is all equal to 1,080, because we just showed that every single triangle that we just created is made up of angles from the octagon. So if I'm looking at triangle 6, I have this corner that's represented from that angle of the octagon. I have this entire corner and then a fraction of that corner too. So every triangle made faces a fraction of one of the angles of the octagon. So when I combine all those 180 degrees of a triangle, I'll have the sum of all the angles of the octagon. If you happen to triangulate in a different way, where you are just connecting opposite vertices, let's get that one right through the middle there. There we go. Connecting opposite vertices, now you find out that I've made 1, 2, 3, 4, 5, 6, 7, 8 triangles, which is different than before. Still the same shape, but why are we making more triangles? Well, we kind of created all of those angles. We took a third of every triangle. So a triangle has 3 corners. 1, 2, 3, 1, 2, 3, and every corner, every 1/3 of all of those corners are now created in this interior circle right here. So I have all these angles right in the center that weren't part of the octagon originally. So when I made my 8 triangles, 1/3 of those 180s were contributing to angles that were never part of the original octagon. So where this becomes a problem is just we need one extra step to solve our solution. So here I would take 8 times 180, and then I would subtract 360. I'm subtracting 360 because of all of these angles from all of my triangles made a complete 360-degree circle. So now this accounts for all those extra angles that I made. So it's an extra step, but you'll still get the exact same answer of 1,080 if you crunch through 8 times 180 minus 360. One final triangulation technique that I had never thought of, but I saw some people working through, is this zigzag version of triangle making. And the way it would start is just kind of going through our lines. We start with one vertice and go to the nearest non-adjacent one, and then straight across, and then up to the next non-adjacent, straight across, then up to that final angle. Looking to see, we still have 6 angles created from our octagon, so we still have 6 times 180 to equal 1080. And so this method works out really well. What I wanted to try was, does it work with odd-sided shapes? So here we have a heptagon, 1, 2, 3, 4, 5, 6, 7. 7 sides gives us a heptagon. And with this method, we would still see 1, 2, 3, 4. So 5 triangles being made, 1, 2, 3, 4, 5. So this would give me 5 times 180. Oop, that's a sloppy 180. So 5 times 180, and that would get us a final solution of 900, which is exactly what a heptagon should be. So we have 2 ways that we should be triangulating, that we can just do number of triangles times 180, and that can be our zigzag or our one vertice to every other vertex. What doesn't work so well was that idea where we had to cross and, like, if here, let me get rid of these and start showing all that crossing technique, where if we did something like this, especially for odd shapes, it doesn't work out as well because, one, I can't connect it to the other vertice, but now I've created 1, 2, 3, 4, 5, 6, 7 triangles, but added those extra 360 there. So it's 7 times 180 minus the 360. Still a very valid method, but it takes a little extra time, and we got to make sure all of our angles are accounted for. The last thing we're going to be looking at are individual interior angles and individual exterior angles of regular shapes. Regular shapes mean that every side length on that shape is the exact same length. So if a shape is regular, that means that every side has the exact same length. If you see these notations on the side, I just put a little tick mark. If you see one tick mark on one side and then another on this on a different side, that means they're the same. So if I put 2 tick marks here and this was regular, then everyone should have 2 tick marks to designate that each side length is exactly the same. So looking back to those, if we look at regular shapes, we need to figure out the interior angles of each shape. We found out that we had, so as we look through interior angles, for just this octagon, we said that octagons have an interior angle sum of 1080 degrees. So if we look at that, what I can do next is divide that by 8, because there's 8 total angles in a octagon. And when I divide 1080 by 8, I'm left with each angle being 135 degrees. So now that I know that each angle is 135, because I can assume that in this regular shape all angles are exactly the same, which is going to get us that definition of regular. If I can assume that, then what comes from this next one of exterior angles comes from, okay, if the interior is made up of 135 degrees, then the exterior is made up of whatever the supplementary angle is. So now I'm looking for the supplementary angle of 135. So now I know that 180 degrees forms this straight line, and 180 minus 135 will give me each exterior angle. And so now what I'm looking at is I would see this is equal to 45, and now I've solved for every interior angle. Every individual interior angle is 135. Every individual exterior is equal to 45. So our next step moving forward is to figure out interiors and exterior individual angles, and we can use those sums to help us figure those out. Just want to recap one thing really quick. Yesterday we went through really quick the equation for finding a sum of interior angles. And once you find the sum, we can figure out each individual angle and each individual exterior angle. So we just want to go through those equations. We talked about it yesterday, but just want to recap. What we said is that as we triangulate, when I pick this vertice to start, I can make 6 total triangles. 6 is 2 less than 8. Those 2, the reason that's 2 less is that we get this vertice and this vertice that were not accounted for. So we have 2 less triangles than we do vertices. So what we found out is that if I can take, and we saw this throughout every shape, whether it was a triangle, quadrilateral, heptagon, hexagon, octagon, any shape. It could be a 13-gon, a 45-gon, whatever it may be called. But however many sides that there are, we know that we can make 2 less triangles because of those leftover 2 adjacent vertices from wherever we start. So our equation then started with s minus 2, where s is the side number or the number of sides on that shape. And then we just took those. That equals the number of triangles that we can make. We know that triangles are equal to 180 degrees in terms of interior angles. So then let's combine these two pieces of information. So if I have S minus 2 triangles, I can then multiply that by 180 to get my total sum. So at this point, here is our final equation. That when I take 2 less than the number of sides, that's the number of triangles I can make. And at each triangle is 180, so then this gives us the sum of our interior angles. So just a quick recap video about what we talked about and a guide and a resource to go back through in case you get stuck. Hope this helps. Adios.